In the past few years, semantic segmentation-based unsupervised domain adaptation has been attracting the attention of computer vision researchers. Many methods have been proposed and achieved remarkable performance. Unfortunately, most of them learn from only one distribution produced by a single model, and the performance is therefore upper bounded, leaving space for improvements. Today, I'm going to talk about the importance of the Ensemble-Distillation method for combining a set of semantic segmentation-based UDA models and introduce a new Ensemble-Distillation framework to address the aforementioned problems. This is the overview of today's topics. First, we will walk through the background knowledge about semantic segmentation-based UDA and provide the motivation behind our work. Then, we will introduce the proposed framework and the key components that provides enhancement to our framework over the baseline methods. Finally, we provide our promising experimental result on the two benchmarks and demonstrate the benefits of adopting our method. The key concept of semantic segmentation-based UDA problems is the generalizability of a segmentation model. Specifically, in the experimental settings, we have access to the image label pairs from an annotated dataset, referred to as a source domain, but only the images from an annotation list dataset, referred to as a target domain. The objective is to train the model using only the ground truth from the source domain and achieve good performance on the target domain. Several UDA methods have been proposed to bridge the domain gaps, which include adversarial training, self-training, data augmentation, or the combination of the three. These methods have demonstrated how a single model is able to learn to generalize to an annotation list target domain. Recently, in light of the potential benefits of combining multiple UDA models, a number of works have attempted to borrow the concepts from ensemble learning. These works demonstrated how a group of UDA models can be trained simultaneously in an end-to-end fashion to learn from different distributions of semantic information, and then meanwhile transferring the knowledge to a compact student model. Despite their successes in bridging the domain gaps with multiple learners, these ensemble methods often lack flexibility, as any modification to the teacher ensemble requires complete retraining of the whole framework. To address such a problem, the concept of ensemble distillation can be leveraged, since its focus is on designing an effective distillation process instead of a costly end-to-end ensemble learning framework. Typically, these ensemble distillation frameworks view the members in the ensemble as probabilistic models and transfer the knowledge using expected average outputs. Nonetheless, the robustness of these methods is not guaranteed, as they do not carefully consider, first, the inconsistency in the scale of the output certainty value among the members in the ensemble, and second, the performance variation across the members in the ensemble. For the former, since each teacher model in the ensemble can be trained independently using different methods, the scale of the output certainty value may not be consistent across the ensemble. This may result in a situation that few members' decisions with high certainty values dominate the entire ensemble's output. For the latter, since the performance, either per class or average accuracy, of each teacher model in the ensemble may vary substantially, few underperforming members in the ensemble may cause the quality of the combined prediction to degrade significantly. This problem is especially severe under the context of UDA, since the ground truth labels in the target domain are not available, and the performance of the ensemble in the target domain is actually unknown. The observation suggests that an effective mechanism is necessary to deal with these two issues and prevent them from influencing the quality of the combined predictions. To address the aforementioned problems, we introduce a new ensemble distillation framework and illustrate it in the top subfigure. The main difference between the proposed method and the previous one lies in two aspects: output unification and fusion function. To resolve the inconsistency issue, we argue that the soft prediction should be unified first in the target domain. This additional unification operation ensures that the raw output certainty values from the models in the teacher ensemble do not directly influence the subsequent fusion results. To accomplish this, we unify the soft prediction by converting them to hard pseudo-labels so that they are on the same scale. This operation ensures that the subsequent fusion function can operate on items with a consistent scale, and thus eliminates the impact of the inconsistency in the original certainty outputs. On the other hand, to resolve the performance variation issue, we propose a new fusion function called Chen-Hao fusion, which is designed to explore how the high and low quality segmentation maps can be retained or eliminated. As shown in the figure, the difference between channel-wise fusion and the previously proposed pixel-wise fusion methods is that the channel-wise fusion treats each class channel as the basis for fusion. The channel-wise fusion relies on a fusion policy pi to decide which segmentation maps are chosen to be involved in the fusion process. An example is shown on the top subfigure. For each semantic class C, the policy pi assigns a teacher model T to generate pseudo-label for that class. Such a fusion function has a property that the pseudo-label can have a MRU bounded by the upper and lower envelope curve, as demonstrated in the bottom subfigure. Since the fusion policy pi determines which teacher model is allowed to involve in the fusion, choosing an appropriate policy is therefore crucial to the robustness of our framework. In order to achieve this objective, we design a certainty-aware policy selection strategy. We observe that the quality of the pseudo labels are positively correlated to the output certain values of the distilled student model. This correlation between the quality of the pseudo labels from the ensemble and the student output's certainty values that shed light on the development of a measure that approximates a teacher model's performance without using the target domain ground truth. In practice, an offline fusion policy selection strategy is adopted. Our framework first performs knowledge distillation on all teacher models and transfers their knowledge to T identical students using the unified outputs. Then their output certainty values are measured to obtain the approximated performance of the corresponding teacher models. Finally, the policy that maximizes the student model's output certainty values is selected. Our framework achieves superior performance on the GTA-5 to Cityscapes benchmark, and it outperforms the current best method and the baseline method with a substantial margin of 4.72 and 5.84 MILU, respectively. In addition, our framework also achieves superior performance on the Cynthia to Cityscapes benchmark, as it outperforms the current best method with a substantial margin of 4.52 and 5.14 MILU, respectively. We then conduct an additional experiment to verify the proposed framework's robustness. In the experiment, a number of underperforming members are added to the ensemble. In our setting, these underperforming members are trained in source domain only. As shown in the left subfigure, the MRU of the baseline method degrades from 51.34 to 45.89, while the proposed method is able to maintain its performance. In addition, we show that our framework is flexible when it comes to choosing the teacher model. As shown in the right subfigure, the performance of our framework can increase as more different teacher models are included in the ensemble. In particular, our method is able to achieve 59.25 MILU on GTA-5 to Cityscape benchmark if the student model is added back to the ensemble for 3 rounds of ensemble distillation. Finally, the visualized output demonstrates the effectiveness of the proposed method.